Hey guys, today we're going to talk about equations of planes in 3 space. So in order to determine the equation of a plane, we need to know two non-collinear vectors that are parallel to the plane, and in order to define that position of the plane in space, we also need a point that is on the plane. There's a couple different ways that we might be presented with this information. So we could have a line in the plane and a point not on the line. We know that from our previous lesson that a line actually contains a position vector and a direction vector. So the line will contain information about a point inside the plane and a direction vector, and then we need a third point. We can also determine this information with 3 non-collinear points, 2 intersecting lines, or 2 parallel and non-coincident lines. So in 3 space, this just means that the lines might be parallel, but they're not the same line. So let's take a look at the different ways that we can express an equation of a plane. So similar to how we can express the equation of a line in 2 space, and in 3 space, we simply need a position vector out to the plane, and then we'll have 2 direction vectors with parameters s and t in front of them. And basically what this does is it can generate all possible points on the plane. So the other important part here is that our 2 direction vectors need to be non-parallel direction vectors that are parallel to the plane. And then we can get the parametric equation of the plane by simply separating out our vector equation into its x, y, and z components, leading us to have 3 parametric equations with the 2 parameters s and t. Now, typically when we talked about lines in 3 space, we were able to express these also as symmetric equations. But if you remember, symmetric equations require us to isolate for the parameter of the line. Now, in planes, we have 2 parameters, s and t. So it's actually going to be impossible for us to isolate for a single parameter, considering that there's 2. So there's actually going to be no symmetric equations of planes in 3 space, only for lines. And we're going to take a look at the scalar equation of a plane in our lesson tomorrow. So we're just going to focus in on vector and parametric for today. All right, let's take a look at an example. So we've got 3 points, A, B, and C, that our plane passes through. And our goal here is to write the vector and parametric equations for our plane in 3 space. So as you remember, we need, in order to create this vector equation, we need a position vector and 2 direction vectors. So let's just choose any one of these 3 points, it can be A, B, or C, to act as our position vector from the origin 0, 0, 0 out to the point. So let's say, for instance, maybe we choose for our position vector point A. So that means that r naught, or our initial, is going to be the vector from the origin out to point A, which is going to be -1, 3, 4. Okay, you can choose any 3 of these points to act as that position vector for you. Now we want to choose 2 direction vectors. So let's say maybe our direction vector number 1, which we denoted as A in the formula above, maybe we can find this using the vector that connects points A and B. So remember, we're doing tip components minus tail components, so B minus A in order to find this. So we'll get 3, -1, -3. And our second one, we can use A and C or B and C, but I can't do like something like BA because that is basically just another vector that is collinear to AB. So I don't want to use BA or AB again. So the options are AC or BC. Let's say maybe we use BC for the next one. So I'm going to do C components minus B components, giving me -2, 2, and -2. And we'll always take our direction vectors wherever possible and just reduce them into lowest form. So if you notice that there's like a common multiple here, I can actually reduce that because I'm simply just looking for a vector that's parallel, and the reduced version of this is also parallel. So this vector isn't necessarily equal, but if we reduce, we'll get direction vector -1, 1, -1. Okay, so that gives us all the information to create our vector equation. So let's put it all together. Oftentimes we will denote the equation of a plane with the variable, or not variable, but with pi. And then lines we usually denote with like a scripted L. So our plane is equal to x, y, z, or you can use the resultant vector r. And then you're going to do your position vector and t times your first direction vector plus s times your second direction vector. And there's our vector equation for our plane. Now I want to hop over to Geogebra so that you guys can kind of visualize what's happening here. All right, so here on Geogebra, I have taken a second to graph our points A, B, and C. So you can kind of imagine here that if I were to rest a surface on these 3 points, then these 3 points are defining a plane. And what we just found are vectors AB, which is this vector that connects A to B, and vector BC. And we also took a second just to reduce that vector to -1, 1, -1. Or I believe in ours it was, oh no, it's the same. So I'll show you what that looks like. So basically we can kind of see the vector here. Remember that the direction vectors that we're working with are simply vectors that are parallel to our plane. So we can definitely see that that direction vector that we found, -1, 1, -1, is in fact parallel to the plane. Okay, so now that we have that information, we put it all together and we can see the plane that lies on this surface. And here's the plane here. So I found the plane that goes through point A, which is what we used for our position vector. And then I used our 2 direction vectors, u and v. You can also use w, and if you kind of notice here, so I'll take away vector v, I'll put on vector w, and I'm going to change that in my plane formula here. And you'll notice that I actually get the same plane. It still goes through those 3 points, and we don't necessarily need this direction vector visible. But basically we can kind of see how our plane works in 3 space here. Okay, whenever you put a plane into Geogebra, it will change the equation into scalar format. So this is a really good way that you can check your work once we get into tomorrow's lesson. All right, so moving forward, we're going to express our plane in parametric format now. So in order to find our parametric equations, we are simply going to separate out each component. So I'm going to separate out the x components, which will be these guys. Keep those scalars there as well. So it'll be plus 3t minus s. And then y is going to be these guys with their parameters as well. And then z. These 3 pieces of information here. All right, so there you have it, the vector equation of the line, or the plane, I should say, and the 3 parametric equations that make up that plane. Let's take a look at another example. So here we're going to be given the 2 direction vectors and a point on the plane, and we're going to start by writing vector and parametric equations of this plane. So this should be pretty easy since we already have this in terms of a direction vector, and we have a point which we can use for a position vector. So we're going to say pi is x, y, z. That represents all the x, y, z vectors that can go out from 0, 0 to points on our plane. And we're going to take this position vector, will be from the origin to the point 3, 7, 0, and add t times those direction vector, or the first direction vector, and s times the second direction vector. Okay, and then if we separate this out into parametric equations, it's going to be 3 plus 8t plus s. Y will be 7 minus 5t minus 3s. And z, because that's 0, we're not going to write that, but we are going to do 4t minus 2s. Now we want to determine if the point -10, 8, -6 is on this plane. So we're going to take our parametric equations. We're going to sub in x, y, and z to start. So x is -10, y is 8, and z is -6. Okay, and I'm just going to simplify these one little bit by taking these constants in the x and y formulas and moving them to the other side. So here we'll get -13 equals 8t plus s, and here we'll get 1 equals -5t minus 3s. Z is already set up for us here. All right, so I have 3 equations and 2 unknowns in this question. And the thought is that if I can use 2 of the equations to solve for the t and s, then if I sub it back into the third unused equation, I should end up getting a true statement. So I should end up getting left side equals right side if that point in fact does lie on the plane. So let's label our equations. I'm going to call this 1, 2, and 3. So I'm going to take 1 and 2. Or you can take any combinations here. I think 1 and 2 should be relatively easy because I can just multiply this by 3 in order to make the coefficients of the x's both 3, and we'll work from there. So I'm going to do equations 1 and 2, and we're going to multiply equation 1 times 3 to get -39 equals 24 t plus 3s, and we're just going to stack them on top of each other here so that we can do an addition or subtraction with them. Now this one has one positive 3s and one negative 3s, so I think we can eliminate the s's by adding the equations. So we're just going to add straight down here, so using elimination, and the s's are now gone. So if we divide that 19 out, you should notice that you get a t value of -2. Okay, and you're going to sub this back into either equation 1 or 2 in order to find s. So we're going to sub t equals -2. Let's just say we sub it into, shouldn't matter, let's sub it back into 1. And we'll solve for s. So s here is going to be equal to -13 plus 16, which gives us 3. Now that we've done that, so notice that I've used equations 1 and 2 only. So this would be your first step, this would be your second step. Third step here is we're going to check these values for t and s in equation 3. And if we get a true statement, this means the point lies on the plane. If we get an untrue statement, then our point does not lie in the plane. So using equation number 3 here, I'm going to sub in t as -2 and s as 3. And I just want to see if the right side, when I simplify it, is equal to -6. So I think here we're getting -8 minus 6, and that gives us -14. So these are not equal. And because those are not equal, it tells us that the point does not lie in the plane. Okay, so use substitution or elimination in 2 of the equations and save the last equation to check your parameters s and t to see if you get a true statement. Okay, let's move on to the next part here. So part C asks us to find the coordinates of 2 other points on the plane. So you can do this from the vector equation or also from the parametric equations. All we're going to do is basically just choose values for t and s. They can be any values for t and s that you want. So let's say, for instance, for the first part, maybe we'll choose s equals 1 and t equals 1. So in our parametric equations, that means x equals 3 plus 8 plus 1, just subbing those right in, and 5 minus 7 minus 3. And for z, 4 minus 2. Oops. Oops, I didn't plug my value in here for t. I meant to put 1 there. Okay, so we'll get 12, negative 1, and 2 as our first point. And because it's a point, we're going to write it with round brackets rather than square brackets. Okay, and then you can choose any other s and t that you want. Let's say we choose, I don't know, maybe we'll go t as negative 1 and s as 2. And then we're going to plug that again into our parametric equations and simplify. So we'll get 3 plus 8 times negative 1 plus 2. 7 minus 5 times negative 1 minus 3 times 2. And 4 times negative 1 minus 2 times 2. So take a second and simplify those. And you should end up with 3, 6, and negative 8. So here's another point that is in our plane. Okay, and if we wanted to, we could even go back to Geogebra and plug in these points. So let's try 12, negative 1, and 2 in our plane. I'm just going to add a point in here. Oh, and hold on, did I do something wrong here? Oh, this is actually our plane from question 1. So I'm just going to take a second, I'll graph the plane from question 2, and then we'll test it. All right, so here we can see our plane is graphed. You'll notice over in the legend over here, I've graphed the point 3, 7, 0. I've also graphed the point that we are checking is on the plane, and I have our 2 direction vectors, and then I've graphed the plane here. So you can actually see everything here. You can see the 2 parallel direction vectors, and you can see the point that is on our plane, which defines the plane, and the point that we're checking is in the plane. So you can actually see that those are exactly in the plane. And the last part of our question here asks us to find the x-intercept of the plane. So I'm going to utilize those parametric equations one more time to do this. And if we think about x-intercept, where the graph crosses the x-axis, that should mean that that is where y and z are equal to 0. We know back from our regular Cartesian plane, if I have an x-intercept at 2, let's say, that's where y is 0. So same thing goes for 3D. If I'm looking for x-intercept, that's where the other 2 y and z are equal to 0. Okay, we would do kind of a similar thing for y-intercept. We would set x and z equal to 0, and then for z-intercept, we would set y and x equal to 0. So basically, I'm just going to take the parametric equations, and I'm going to kind of copy them back out again, but I'm going to set y and z equal to 0. And what we can do from this, I'm going to use these 2 equations here. We're going to call these equations 1 and 2. What we can kind of do with this is set up 2 equations and use elimination kind of like we did before. So the first thing that I'm going to do is just move this 7 over here. Usually we have constants on one side, so we'll get negative 7. And we'll have 0 here. And the goal when you're doing elimination is to have 2 variables equal to one another, or the coefficients of 2 variables. So I can choose the t's to make the same or the s's to make the same. So I think I'll just take this guy and I'll multiply this whole equation by 2, and then we'll take this equation and multiply this all by 3 to get 2 equations where the coefficients of the x's are the same. Did I say x's? I don't know. If I said x's, I mean s's. Okay, so coefficients of our s's are the same. And now you just need to choose whether you have to add the equations or subtract the equations in order to make this 0. So here we have two negative 6's, so I think we have to subtract these in order to eliminate the s's. So negative 14 minus 0, that's just going to stay as negative 14, and then this will become negative 22t. And if we've done it correctly, the s's should cancel out. So we'll have negative 6s minus negative 6s, which is 0s. Okay, so let's isolate for t here. We're going to get negative 14 over 22, and you can go ahead and reduce that. So we'll divide 2 out from each of these, and we'll get negative 7 over 11. Okay, we're going to sub that back into one of our two original equations in order to find s. So let's say we sub it back in here. So 0 equals 4 times negative 7 over 11 minus 2s. And we're simply going to solve for s here. So multiply in your 4. And we'll say 2s equals negative 28 over 11. So if we divide out that 2, we're going to end up with oh, sorry, I made a little mistake here. We've got, these are positive, so I was just thinking this doesn't really make sense. Sorry, 14 and the negative 22, the negatives cancel out there, so just fix that. Okay, so then when we divide out here, we're getting 14 over 11 for us. And since we've solved for those for where y and z are equal to 0, we're going to sub this back into the equation for x. So given these two pieces of information, we can now figure out our x-intercept. So we're going to sub in 11 over 7, and this will really just be 14 over 11 because it's 1s. Okay, and then you're basically just going to leave this in exact value where possible. So if you find a common denominator here, you'll end up with 103.11. So that means that our x-intercept can be found at the point 103 over 11, 0, 0. Okay, let's take a look at one final example here. Our third example is a plane with x-intercept 2, y-intercept 4, and z-intercept 5. We are going to find the vector and parametric equations. So let's just write out our points to start. We have 2, 0, 0. We have 0, 4, 0. And 0, 0, 5. So you're going to choose one of these as your position vector or your r0 vector. Let's say maybe we choose 2, 0, 0. And then we're going to create our two direction vectors. So let's say we maybe choose these two to make up our first direction vector. So I'll do 0 minus 2, 4 minus 0, and 0 minus 0 to get negative 2, 4, 0. And then we'll reduce it. Just helps us kind of all get the same thing no matter which order we've put it in. And then, although we will all kind of get different values depending on which vectors we choose. And then maybe we'll choose this vector and this vector for our second, this point and this point for our second vector here. So we'll have 0 minus 0, 0 minus 4, and 5 minus 0, which will give us, oops, sorry, this is supposed to be 0, which will give us 0, negative 4, positive 5. Okay, you may get the opposites of these, like if I chose the vector that connects these 2 points, but in the opposite direction of the one that I just calculated, you may get 0, 4, negative 5. That's totally fine. And then we're going to create our vector equation. So our vector equation typically will represent the plane with pi. Maybe I'll just write this out here. And we're going to have x, y, z. Put your position vector, 2, 0, 0. Have your parameter times your first direction vector. And your parameter times your second direction vector. Okay, and then we're also tasked with finding parametric, so we're just going to simplify or separate this out into our three components. So x, y, and z. Okay, so there's our vector, and there's our parametric. Oops. And then part B asks us a separate question. So it says we're going to find the vector and parametric equations of the plane containing the line x, y, z equals and so on. And it needs to be parallel to a second line with this information in part B here. Okay, so if my plane contains the first line, that means that it contains this point, 0, 3, negative 5, and it contains this direction vector. And if it's parallel to the second line, it doesn't necessarily contain this point, because that's a point that is maybe in a line that hovers above the plane, but it does have a direction vector which is parallel to the direction vector of the line. So I can easily find my vector equation of my plane by using the position vector for the first line, which is essentially just a point on the plane as well. So 0, 3, negative 5. And then I'm going to use a direction vector from each line. So the first one will be 6, negative 2, negative 1. And the next one will be 1, negative 3, 3. And that's really all we have to do for this one. So those are my pieces of information. So that's for our vector equation. And we also want our parametric equations. So just take a second and separate out your x, y, and z components here. And there you have it. I'm going to hop over to Geogebra here and just show you how this plane here is connected to the two lines that we just talked about. Okay, so here I have graphed our two lines. Line G, which you can kind of see labeled there, is our line that is just parallel to our plane but not in our plane. And line F is going to be the line that's actually inside the plane. So let's take a look at what this looks like when we put it together with our plane. So if you're doing this, just to check some of your work, I want to put the point P in here, and then you need two direction vectors, and the ones that we used were A and B. So what you need to do is type the word vector and A, separate by a comma, and then vector B, and we should see our plane pop up here. So you should see that when we look at our plane, let's just zoom out just a little bit here, you can actually see line F inside that plane. And if we show the point here, you can actually see the point inside the plane as well. And then for our second line, you can simply see that this line is parallel to our plane, but it's not inside our plane. And that means that this point as well is inside the second line, but it's not in the plane itself. So we ended up using the point 0, 3, negative 5 in the plane, and then the direction vectors from each of the lines. So that's kind of visibly what you should be imagining when you're imagining what you just calculated.